Now that we've seen Young's double slit experiment with interference, and we've seen the idea of diffraction in terms of a single slit experiment, we can ask the question, what actually happens when we shine through a double slit? Because aren't two double slits nothing more than two individual single slits? And the answer is yes, they are. So we start off with a double slit, and what we've seen before is we get a nice little pattern where we get the bright and dark bands forming from plain light coming in and oscillating back and forth, and we get dark and bright bands. And the pattern, this is an ideal pattern for it, for two infinitesimally small slits. But the conditions for the maximum minimum, as we've seen before, is d sine theta, the distance between the two slits, times the sine of the angle, so how far to the right or to the left we're going, is equal to an integer number of wavelength. And similar for the minimums, where the dark bands are, we get d sine theta is equal to n plus 1/2 times lambda, where n again is an integer. One thing we didn't cover before, and we're just going to tell you outright without any proof, is that the intensity for this interference pattern goes as the intensity for a given angle is equal to 4 times the initial intensity times the cosine squared of beta. And beta is nothing more than pi d over lambda sine of theta. So coming from what we have up here, we just rearrange it, throw stuff in there, and this is what we call beta. So the intensity will fall off as the angle changes, and it tends to be a slow decay that comes across. And the picture is not exactly to scale for it, but this is what we get. Now if we go back to the single slit experiment, we saw that because of Huygens' principle, we're going to get the wavelets. These wavelets are going to interfere from a single slit. So if we look at what happens there, we're going to start off with a strong peak in the center because everything on the left and everything on the right will constructively interfere with their mirror image of each other. And at some point, one side is going to interfere with the other side completely. You know, this point here might interfere with this point. This point might interfere here, point over here might interfere with there. And we're going to get minimums, and this is going to be symmetric, so we're going to get this wonderful pattern. It's called a sinc function, and it has the form of the intensity is proportional to the sine of theta over theta, quantity squared. So we call it a sinc function. It's a pretty well-known function that we see. And it gets us a really kind of cool pattern. Well, now what we're going to do is we're going to put both of these together. And if we look at it, we start with our original double slit from an infinitesimally small slits pattern together, and we get this oscillatory pattern. And what we're going to do is we're going to superimpose the diffraction pattern from the single slit on top. So the double slit and the single slit is now in the blue. And when we put the two of them together, we're going to we'll see this big, the blue one outside will have this kind of bulk characteristic, and we see that on an individual level it's going to be up and down. So the dotted line doesn't actually exist. It's the red line that's all that actually happens. So we get dark bands and light bands and dark bands and light bands, and then they get weaker, and then they get stronger, and they get strong, and then 0, strong, 0, then back down to 0, and then back and forth. So the bright blue band that we see here, we call this an envelope. It tells us kind of on a bulk scale what's happening, but really what's happening is these individual ones. So this is what happens when we interfere when we have the two different types of interference happening. We have the interference from the double slit and the interference from the single slit diffraction happening. So if we actually run through the numbers on this, the intensity happens that we get the intensity of the double slit, the interference term, and we also get the diffraction term. And this, what we call, modulates the amplitude. So that's what the modulation is what we call the envelope. And we put both together, and then we can define alpha and beta, where beta is pi d over lambda times sine of theta, and alpha is a over lambda times sine of theta, where lambda is the wavelength, D is the slit separations, and A is the single split opening, how wide it is. So all in all, this works out, and we can actually see it in real-world examples, but this is what happens, and we can see that these two principles, these two characteristics of light interfering with each other do happen together.